So today the topic of the lecture would be something like, oops. Well, we are going to continue with hydrodynamics. Hydrodynamics. And today we are going to focus on viscosity. Well, probably I'm going to write every buzzword I'm going to use during today's lecture. So that would be viscosity, Poiseuille formula, Poiseuille equation, Reynolds number, boundary layer, what's here? Lifting force of the wind, or a wind, probably A is better, of a wind, lifting force of a wind. So lots of topics to cover for a short lecture. So of course I'm not going to do a rigorous explanation to all of this. Well, probably I would start with some kind of a problem which occurs if you study the motion of ideal fluid around some objects. The paradox is called D'Alembert paradox. The D'Alembert paradox. And the paradox is formulated as follows: that if you have some sort of a body and you have a fluid moving around it, and assuming that there is no friction, that this is an ideal fluid, it goes around and forms a laminar flow around this body. And as was calculated by D'Alembert, the drag force which acts on this body should be zero. That's it. Drag force is zero. So there is no drag force produced by the motion of the fluid around the body, which quite contradicts our everyday experience. Like, for example, if you go to the pool and then try to move your hands in the pool, in the water, then you will see that there is actually a drag force. So there is some resistance from water. Nonetheless, in the stationary conditions, it was rigorously derived, mathematically mathematically proven that drag force is zero. So that led actually to a huge crisis in the development of hydrodynamics, and as far as I understood, that led to the separation of the subject into hydraulics, where you study something which you observe but cannot explain, and hydrodynamics, or like fluid mechanics, which kind of explains stuff which you cannot observe. So that's a real crisis in hydrodynamics. And I think the one step which was made to solve this crisis was made by German scientist Brandt, who suggested that around any object, if you study the flow of something around the object, there is a boundary layer. And in the thin boundary layer, the viscosity, even if it's small, the viscosity produces quite a great force on the object, and that leads to formation of the drag force. So he said that even if the viscosity is small, there is a thin, well, that depends on the conditions, whether this layer is thin or thick actually, but if its viscosity is really small, then that boundary layer becomes thinner and thinner. But there is thin boundary layer, which produces significant force. Okay, so that means that viscosity plays a very huge role in the motion of fluids around bodies, and even if it's small, it is the origin of the drag force at least, and the origin of many other interesting phenomena in hydrodynamics, like turbulent flow. And also, well, we can go back to this D'Alembert paradox. It says that there is no drag force. We can actually even formulate that not only there is no drag force, there is no lifting force here. So in order to achieve some lifting force, you need viscosity. So the airplanes are moving in the sky and don't like drop onto the surface of Earth. One of the reasons for this is that there is viscosity of air, even if it's small. It's really important to have viscosity. Okay, so let's now move to the concept of viscosity. What is this? Oh, I have a mistake here. Viscosity. So we need to give some mathematically rigorous definition of this concept, because you can understand that actually viscosity, well, in terms of your, in terms of what you see, is that the liquid, for some reason, resists any attempt to change its shape. So, for example, if you have a glass and you pour some liquid into this glass, then actually what happens is that after some time, the liquid in the glass forms this shape. And actually, if you pour water and if you pour, for example, mead, then that would give you, well, different speed of this process. So you would achieve this shape after different amounts of time. And the amount of time which is required to change the shape of the liquid is, well, depends on this property, which is called viscosity. But nonetheless, we need to give a more rigorous formulation for that. And to give a rigorous formulation, we should consider a so-called coet flow. It's again after the surname of the scientist who studied this type of the flow, and those of you who major in aerospace, you would have more time to spend studying these types of flow and the different conditions. But actually it's quite simple. You assume, in a simple case, you assume that you have two infinite planes, or two infinite plates, yes. So, and one of them is moving with respect to the other one with some velocity v, which is parallel to the plate, and in between them you have a liquid. And due to the friction between the liquid and these plates, the liquid starts moving along the upper plane. So it turns out that it forms some sort of a velocity distribution in between these two plates. So in the end, we assume that actually the velocity of the liquid near the upper plate, near the top plate, is equal to the speed of the plate, while the velocity of the liquid near the bottom plate is again equal to the velocity of the bottom plate, which is 0, and also we have some sort of a distribution in between. And it turns out that if this separation is not too large, then actually the distribution is as follows. So it's linear distribution. And also you can make a measurement. So actually, in order to keep the upper plate moving in this condition, you need to apply some force, and that force actually leads to the so-called shear stress tau. So if you divide the amount of force by the area of the upper plate, you would get a shear stress. Shear stress tau, which is equal to the ratio of force to the area. And it turns out that this shear stress is equal to some coefficient, this is Greek letter eta, multiplied by the derivative of this velocity with respect to the direction which is normal to the plate, dv to the dn. And well, in this case, actually, in here, this equals to v over d, where d is the separation between the top and the bottom plate. Okay, this number which appears here is called the viscosity coefficient. So viscosity coefficient describes the inner friction which exists in the liquid, and viscosity is, by its nature, it's an irreversible effect, because, like, for example, if you have some layers of liquid moving with respect to each other, then if you leave it as is, then after some time you would observe that there is no respective motion. So this respective motion is being damped by the viscosity, and that pretty much looks like the establishment of thermal equilibrium. For example, if you have different temperatures, then after some time you see that there is no difference in temperature in the equilibrium condition. So the same is with the viscosity. So if you have relative motion, this relative motion is damped by the viscosity. So viscosity is the irreversible kind of a force, and that makes the viscosity fundamentally different from elasticity of solid bodies. So if you compare the resistance to the change of the shape in liquids and solid bodies, you would see that actually they are somewhat different. Well, liquids can change their shape, solids can do so too, but they resist to the attempts to change their shape. While the liquid does so through the viscosity, solids do so through elasticity. So if you apply some force, there is some counteracting force which is proportional to the elongation or shrinkage of the corresponding solid body. But while in solids this type of a force is elastic, so that means that if you, like, for example, if you relieve your force, if you don't act with your force anymore on a solid body, it will restore its shape. So that means that there is reversibility in this. But, well, at least the reversibility up till some kind of critical elongations where, like, your solid body would crack into something or be destroyed. So, of course, it's more complicated. But as long as we study some small changes of form, then it's elastic. while in the liquid, everything is irreversible. So this is actually the main difference. Okay, so that's the viscosity coefficient. Now we should move to something like we continue studying some very simple kinds of flows of this liquid. And one of them, probably the simplest, is that if you have a long pipe and you have a liquid flowing through this long pipe, there would also be some distributions of velocity. And as you see, there is a difference from the previous case. In the previous case, I had upper plate which moves with some velocity. Well, in here, my pipe is completely at rest, so it doesn't move. But nonetheless, the liquid moves here, and the reason why the liquid moves through this pipe is that I have a pressure difference. So in here, I have pressure equal to P1. On the other side, I have pressure equal to P2. And, well, in order to force my liquid to move from one direction to another direction, I need for my pressures to be in this kind of a relationship. P1 should be greater than P2, so I have pressure difference actually. So it's the pressure difference which forces the liquid to move. And well, let's assume that I know, for example, the radius of my pipe. So what I want to find out is that how much of the liquid would flow through my pipe. So I kind of understand that as I apply more of the pressure difference in between the inlet and outlet of the pipe, then more of the liquid would flow through it per unit of time. So what I want to determine is the amount of volume of the liquid which flows per unit of time through my pipe. And let's say I have some additional assumptions which I want to solve this problem. So this problem is quite complicated in the general case, but if I make some additional assumptions, then the problem becomes like manageable in terms of difficulty. One assumption is that I have stationary flow, as usual. Flow. The other one is that my flow is laminar. Laminar flow. Well, actually, there can be two types of flow. One of them is laminar, another one is turbulent flow. And the turbulent flow is, again, the observation says that if my delta P is large, so far I don't understand what the word large means, but nonetheless, that if my delta P is large, then the flow is turbulent. The flow is turbulent. That would be the question actually, what large in here means. So what large means in this pressure difference. But indeed, so let's assume first that we have a laminar flow, and then we are going to continue the discussion. So we don't know what large pressure means, but nonetheless, let's assume it's small. Okay, so well, that allows me to introduce a function which kind of describes the velocity profile inside the pipe. So I can say that my velocity is a function of the distance to the axis of the pipe. So I assume that actually my velocity profile is the same in the different cross sections of the pipe. I can kind of say that this is related to the continuity, because if I have this laminar flow in here, then if you remember the continuity equation, it says that that the product of the velocity or to the cross-sectional area of this streamline should be constant if I talk about liquid. And now I talk about liquid, so I assume that my density is constant. Well, since I don't have any kind of a change in the cross-sectional area throughout my pipe, that means that my velocity in all of these cross-sections would be constant. Okay, so now we are ready to solve it. And in order to do this, we need to study the motion of the fluid in one of these streamlines. So if I take one streamline, let's see what kind of forces act on the liquid on this streamline. Well, first of all, I have a pressure force acting from this side, so that would be P1 times dA normal. So that's amount of the pressure force going from this side. I have the same pressure force from this side, P2 dA perpendicular. And also, by the definition of the viscosity, and since I know that my velocity profile is dependent on the distance from the axis, so this is the sort of the distance I talk about, that means that there also exists a shear stress which acts on this. So the shear stress which goes on the outer side, tau 1, let's say, and also there should be some shear stress from this side, tau 2. Okay, let's choose all of the streamlines, select all of the streamlines whose distance from the axis is in between r and r plus dr. The cross-sectional view of the streamlines I have chosen goes like this. So this is my pipe, the cross-sectional view of my pipe. So this is small r, and this once again r plus dr. So dr is the thickness of the region I have chosen. Okay, so now let's write equilibrium condition for the chosen number of streamlines. So first of all, the forces of pressure give P1 minus P2 times dA, where dA is the marked cross-sectional area, and I can write that actually this dA, so this goes for the cross-sectional area between radius r and r plus dr. This cross-sectional area is approximately equal to 2 pi r times dr. So actually this is a very thin line, so in order to get the area I need to multiply the length of my circle by the thickness of this stripe. So that would give you 2 pi r dr. And now the following, these viscosity forces. So viscosity force number 1, which acts on the outer surface of my selected area, is equal to 2 pi r times L, where L is the length of my pipe, multiplied by the viscosity coefficient times, let's say, dV over dr. Okay, so since I consider the outer surface, so I think this one would be 2 pi r plus dr. So what is this? The first term here is the side area or sidewall area of the cylinder, which is formed by the outer surface of my selection. So my selection goes, this is how it looks like in the cross-sectional area, but it actually is a volume which goes throughout all of my pipe from the inlet to the outlet. So this cylinder is the side area of 2 pi r plus dr times L, and this is the shear stress produced by the viscosity. So I multiply the shear stress by the sidewall area of the cylinder. In the previous example, where I have studied the flow in between two plates, parallel plates, I have said that the force which I need to apply to counter the viscosity is a product of the shear stress by the area of my plate. So you can consider this side area is analog to the area of the plate on my previous example. Okay, another force is 2 pi r times L times eta, and again dV over dr, but while here I had dV over dr at r plus dr, here I have it at r, so that corresponds to the inner surface of my selection. And also it goes in the opposite direction, as I have shown here, because T1 acts in that direction, tau2 acts in this direction. Well, that's assuming that dV over dr is positive. So please be careful with the signs here, because actually dV over dr is negative. So that's why in real case, this vector goes in the opposite direction and this in the opposite. But I assume when I write my formulas, in order to get the correct signs before this, I can check them by assuming that dV over dr is positive and see where these forces go. So if dV over dr is positive, then the outer surface would be dragged in the direction of the flow, while the inner surface would experience a force which actually drags into the direction opposite to the flow. And again, this difference between pressure forces is in the direction of the flow. So altogether, I can write the equilibrium condition, which is Fp plus F viscosity 1 plus F viscosity 2 is 0. I have everything stationary in my problem. That means that all of the forces added up together would give me 0. So the final equation is as follows: delta P times 2 pi r dr equals to, okay, let's get all of the common factors out of this. So that would give us 2 pi times viscosity times L, which is common for both of these forces. And then it goes as follows. In here I have, so since I got two of my forces to the right hand side, that means that this minus gets to the plus. So I would have R times dV over dr at R minus R plus dr times dV over dr at R plus dr and well, so far it looks quite complicated, but you can see that actually in here I have a small difference of the same function, but at different points. So that means that let's say I have a function or some f of r, which is r times dv over dr at that r. So what I have here in the square brackets is f of r minus f of r plus dr. And when this dr is very small, you can actually express this through the derivative as minus dr times the derivative of df over dr. So that's by definition of the derivative, actually. So that means that I can rewrite my equation as follows. Delta P times 2 pi r dr equals to minus 2 pi eta L dr times d over dr, so this means the derivative over r, of r times dv over dr. Okay, the good news about this is that actually I can eliminate this one. So that gives me at the end the perfectly differential equation which describes the velocity profile in the cross section of my pipe. And also I have two pi's to the left and to the right, and actually that's actually nice because I can cancel them out and slightly simplify my equation. So in the end I have the following: delta P equals to minus eta L over R d over dr r dv over dr. Okay, so what we are going to do next is we are going to analyze this equation. Or we are going to integrate this equation. So please bear with it because the answer is quite close. So if I have this equation, that means that I can actually integrate it over the r. So it says that actually that's derivative of some function over the distance to the axis of my pipe is a constant. So that means that I can immediately write the solution. R times dv over dr is, dv over dr is equal to some constant c minus delta p slightly wrong, because I can write it as follows: d over dr of r times dv over dr equals to minus delta p times r over nu L. Let me have a slight check with the previous slides, because I have some, well, I think there is no difficulty here. Everything is correct as far as I see. Yeah, R should be present here. Okay, so delta P times R over nu L. So actually, the derivative over R is proportional to R. So when I do the integration, I can write that R times dV over dr equals to some constant minus delta P R squared over 2 nu L. Now I need to understand somehow to determine the value of this constant, And let's look at this pipe once again. I assume here that the velocity is the function of this distance to the axis, and if I go in here, so if I assume that r equal to 0, due to the symmetry of this profile, actually I can conclude that okay, in here, if I take r equal to 0, that means that the left-hand side becomes equal to 0. And also the right-hand side should be equal to 0. But the right-hand side, only the second term goes to 0, but the constant remains. But since evidently it should be equal to 0, this can only be satisfied if this constant is 0 itself. So now I get this equation. Now I'm continuing with the calculations, and I divide both the left and right hand side by r and get dv over dr is minus delta p times r over 2 eta L. And once again, I have the equation which quite looks like the same as this one. So when I do the integration, I again obtain that the velocity as the function of r is equal to some constant minus delta p over 4 eta L times r squared. But here, this constant is not 0. Because now, once again, if you look at this shape, then at radius equal to 0, the second term goes to 0. But the first term actually gives you the maximum velocity of the liquid in the pipe. And of course, we need to somehow determine this constant c, and this can be done based on the boundary conditions. As I have said, when you have viscosity in the boundary layer, which goes in the exact vicinity of the side walls of your pipe, the velocity should be equal to 0. So it should coincide with the velocity of the solid body. So V of capital R, where capital R is the radius of the pipe, should be 0. And from this, we can determine this constant c. I just insert capital R into my equation and see that this is c minus delta p capital R squared over 4 nu L. So, and this should be 0. And from here, I get that the constant is delta p R squared over 4 eta L. And after I plug this constant into the velocity dependence, I get V of small r as delta p over 4 eta L times capital R squared minus small r squared. Well, this equation actually means that we have a parabolic distribution of velocities inside the pipe. So this is a parabola. Well, usually probably in algebra classes, you had plotted the parabola as something like this. Well, in here we have exactly the same stuff, but the parabola on that plot is rotated by 90 degrees counterclockwise, and that's the result. Okay, well, we had obtained the distribution of velocities in the pipe, but this is not the final answer, because if you look at the beginning of this problem, where I have formulated the thing which I wanted to determine is the volume of the liquid which flows through the pipe per unit of time. So the velocity distribution is very important in determining this quantity, but we need to do some additional calculations. So how can we determine the volume of the liquid, capital V, which flows through the cross-sectional area of the pipe? Okay. So now, once again, let's look at the cross-section. So everywhere we have some velocity vectors which go into the blackboard. And with these velocity vectors we associate the flow of the liquid. And of course, the rate of the flow is different at different points of the cross-section. So where the velocity of the liquid is larger, the flow is faster, and at the points where the velocity is lower, then actually the flow of the liquid is slower, so less of the volume goes at that point. So that means that we actually need to integrate everything. So if I assume that, for example, my velocity is constant everywhere for a moment of time, if my velocity is constant everywhere, in order to obtain the volume per unit of time, I just need to multiply my velocity by the cross-sectional area. And do you understand why should I do this? So why the multiplication of the velocity by the cross-sectional area gives you the volume per unit of time if I have constant velocity throughout the whole cross-section? The reason is as follows. That if my velocity is constant everywhere, then let's say I have chosen to look after some cross-section of my flow. And after the amount of time delta t, the cross-section is displaced by v times delta t. And the volume in here, the volume would be equal to v times delta t times the cross-sectional area A. So that means that if I want to determine dv over dt, I need to divide this by delta t and get v times A. But what happens when the velocity has more complicated distribution throughout the cross-section? And that means that we need to divide our cross-section into small areas and integrate the volume flow of the liquid throughout the whole cross-section. So instead of this v times A, I would have an integral of v times dA, where dA is an element of the cross-section. So in here, I'm going to determine this integral. So Q is integral over the whole cross-section of V times dA. And once again, let's divide the cross-section into small circular stripes. As we know, the velocity depends only on the distance from the axis of this pipe. So that means that throughout the whole cross-section element shown here, the velocity would be constant. So that allows us to simplify the equation. So we would have V of R times this cross-section area, which is 2 pi R times dr. And now I plug this dependence into this integral and straightforwardly calculate it. So this is delta P over 4 nu L eta L times r squared minus small r squared times, and well, in here, actually it's quite convenient for me to do the following transformation. Instead of 2 pi r dr, I'm going to write pi times dr squared. So I'm going to change the variable of integration. And why I do this? Because in my velocity dependence, everything depends not just on the distance r, but on the squared distance. So if I have the integration over the squared distance, it would be more convenient for me. And the reason why I can do this transformation is related to the basic properties of differentials. 2 pi r dr equals to 2 pi dr squared. So if I cancel this pi, that means that dr squared equals to r dr. And if I write it like this, this is actually the well-known formula for the derivative of the squared function. So if you know that x squared derivative gives you 2x and r squared derivative over r gives you 2r. So everything is perfectly justified. Now I do this integration. First of all, I take out the constant from the integral, delta p over 4 eta L. And in here I integrate, since I integrate over r squared here, so that goes from 0 to r. So this parameter goes to r squared. So that means that in here, well, the first part is the integral of the constant. So that's easy to integrate the constant. Okay, pi goes here. And the integral of the constant is r squared times change of this. So at r equal to 0, this is 0. At small r equal to capital R, this is capital R squared. So that goes r squared minus 0 squared. And I need to subtract something here. Probably I'm going to subtract half of this, because r squared dr squared is the integral of the linear function. So that means that this is r to the power of 4 minus 0 to the power of 4 over 2. Okay. Well, this can be easily transformed, so that the first term gives you r to the 4, the second term gives you r to the 4 over 2. So if I subtract the second one from the first one, that gives you r to the 4 over 2. So again, I have delta p times pi over 8 eta L times r to the 4. That's probably the final answer. Let me see if I haven't done any kind of a mistake. Oh, I think everything was okay here. Yeah. Well, usually when this Poiseuille equation is written, so this is Q, it's typically determined in terms of how much of the pressure difference you should apply in order to obtain a given amount of flow. So it's written as follows: 8 eta L times Q over P pi r to the 4. And as you see, the longer the pipe, the larger the pressure difference you should apply in order to obtain the same amount of flow. Okay, sometimes this Poiseuille equation is called Hagen-Poiseuille equation, and the reason is that this equation was obtained independently by two different scientists, and one of them was Hagen. Q is the volume of liquid passing through the cross-section area of the pipe per unit of time. So nothing to do with heat. Just the Q is like traditionally used in this Hagen-Poiseuille equation for this. It has nothing to do with any kind of heat or temperature change. Well, that's confusing a bit, but nonetheless. Well, before I continue, I would like to give a short historic remark about the guy who was D'Alembert, who formulated the D'Alembert paradox, with which I have started my lecture. He was one of the French scientists who were like a prominent figure in the age of enlightenment, yeah. And together with Denis Diderot and multiple other co-authors, he has written an encyclopedia which has contained probably like most of the scientific knowledge available by the time. And his co-author actually visited Russia. He had spoken with Denis Diderot has visited Russia and has a long speech with this Imperatrice Catherine the Great, where he has explained his views on how society should be managed, about this secular society and different branches of power which are independent from each other. And well, after the talk has ended and Diderot went on his way, she said, like somewhere, I have spoken with Diderot, and he says that we should abolish our military, monetary, and judiciary system and live further with some unrealistic dreams. So like the French age of enlightenment in Russia came into the so-called enlightened absolutism, in which we had like absolute monarchy, but with some kind of a technical and scientific progress going on. After that, Napoleon the Great has decided that like, for example, he should enlighten Russia by force, and that came to be like what's known like Patriotic War, the first one. The second one was during the World War II in 1940s. And well, clearly his attempts also have failed. So Russia has remained not too much enlightened state by that time. So that's the history. And actually, as you see, like at different times, scientific figures played a major part. So like they were not like restricted only to doing science. They were philosophers. In case of D'Alembert, he was also a music theorist. So he has also some works related to how music should be done, not only like hydrodynamic flows and something like this. Well, and that shaped like the history, and probably like the age of enlightenment is what has shaped the modern society, because almost in every country, well, this system is being adopted. So not much of the countries remained with this absolute monarchy or something like this. Okay, so that's a historic remark. So actually all of these figures I am talking about, they were like prominent figures of their times, and their influence or impact on the development of humanity is not only limited to the formulation of paradoxes or some truths found only in science, but they do something more than that. Probably you may do something more than that too. I don't know. But actually, the chances has decreased, because the complexity of the knowledge has gone so much further, so that specialization or like measures, well, pretty much determine your your future path. So if you don't change your measure, or probably you will stay limited to some kind of specialities attached to your measure. Because politicians have managed to talk smoother, to talk better than guys who specialize in physics, probably. At the same time, like physicists and mathematicians came up to understand some stuff which are almost completely ununderstandable by the majority of population. That means that in order to get to the cutting edge of the development in any field, you need to spend so much time that it doesn't leave too much for you to develop yourself in other fields. So that's a pity actually, because at that time actually one guy was able to cover almost everything. he was able to do like a political changes. He could be like a great advocate, or like he can be a great political figure, and at the same time he would be a great sportsman and, and whatever else. Right? Now people are not so universal. It's actually like kind makes me missing those times for some reason, but nonetheless the progress is going on, and probably well, the society would remain like, will get more prosperous, even despite that actually the specialization actually brings some concerns. Okay, so now we get back to the Poisson equation, and I have said that it should be applicable only if the pressure difference is not too large, and I have said that I don't know yet, and I can't formulate what not too large actually means. Well, there is an important number which is dimensionless, and that number determines whether you have laminar or turbulent flow. So as I have said previously, this Hagen-Poisson equation is applicable only to the laminar flow, so I need to demand that the flow is laminar. But whether this flow is really laminar or turbulent depends on this number, which is called Reynolds number, RE, and this is determined as, let me say, eta, oh no, density times the velocity times some characteristic distance d over the eta. So in here I have density of the fluid, v is the characteristic velocity. Of course, velocities can be different at different points of space, but there should be some kind of a characteristic value which shows you how large the velocity actually is. And d is, for example, a diameter of the pipe, or the characteristic size of an object in the flow. So some characteristic size in the problem. And eta is again the viscosity coefficient. And as it says that well, the number becomes larger as like the velocity grows. So if the velocity is larger, then the number grows larger. Also, it grows larger with the increase of the density, and it grows larger with the decrease of the viscosity. So the less the viscosity, the larger is the Reynolds number. And it turns out that if my Reynolds number is small, let's say for the flow in the pipe, it was established empirically that if Reynolds number is less than 1000, then we have laminar flow. While if the Reynolds number is larger than 10 to the 4, and then we have a turbulent flow. And in between, if my Reynolds number is in between 1000 and 10 to the 4, then we have some kind of a intermediate condition in which you may have turbulent flow, you may not have, depending on the actual conditions of your system, the history of the flow. So it's not determined. So it can be, but it can also be laminar in some cases. So that means that, well, in here, like if my V is larger, then that means that my Q is larger than my delta P is larger. So that actually means that if I increase the pressure difference in between my inlet and outlet of the pipe, then the Reynolds number would steadily increase. And that brings me to another paradox. During the previous lecture, I have discussed with you the Bernoulli equation, and it said that like it was like rho v squared over 2 plus rho g h is constant. It's for the liquid, but in the case of the gas, it was something like h. Which is probably molar in enthalpy plus mu v squared over 2. Here is the kinetic energy for 1 mole of fluid, plus mu gh, where, once again, yeah, it was molar enthalpy, capital H, and here can be small h, the elevation with respect to the ground level. So that is constant. So that is Bernoulli equation, and it assumes that my fluid is ideal, so I have no viscosity here. If I plug this viscosity into here, then I would get infinite Reynolds number. So that means, at the same time, this equation was derived for the laminar flow. So it basically says that if I have zero viscosity, I cannot have laminar flow, so that means that I cannot have Bernoulli equation with me. That's a paradox. Well, this paradox can be resolved, and well, of course, in any fluid you have a finite viscosity, non-zero, but that means that if I write Bernoulli equation along this Bernoulli integral along the pipeline or along the streamline, that means that if the separation between these 2 points is too large, then it doesn't hold anymore, because the energy loss in here would be comparable to the other energies in the system. So I cannot neglect this theta. So, but if my points are located closer to each other, so there is some distance in here where the Bernoulli equation actually is valid. So as long as I have the separation between the 2 points on my streamline in which the dissipation of energy caused by the viscosity is not large or is much smaller than characteristic energies in this equation, then my Bernoulli equation is valid. And actually, have you had already the laboratory practicum related to viscosity? Yeah. So if you have read through the description of the work, it said that, okay, we have a vessel and we have also a quite long pipe here, and you have measured. Okay, so you collected all of these droplets and you have measured the amount of the liquid which goes through this pipe, and it said that there is some intermediate region in here. So when you have calculated this flow through this pipe, when you have taken the length of this pipe, it was said that you do not need to account a small region near the vessel, because it was a so-called intermediate region, the region where the Hagen-Poiseuille flow is being established. So in here at the start, you have almost uniform distribution of the velocity through the cross section. But in here, due to this viscosity forces, you already have this stationary and invariant distribution of the velocities. So, and as far as I remember, to determine the length of this intermediate region, you have used Bernoulli equation. So it was somehow related to Bernoulli equation. So that allows you to determine like where you can apply and where you cannot apply your Bernoulli equation. For example, Bernoulli equation really gives that if you consider the streamlines of fluid starting from the vessel and going into this pipe, then it says that actually all of the velocities throughout the cross-section of the pipe should be equal to each other, because everywhere the h is approximately the same. And that means that this is, okay, here goes also the pressure, and here also should, and here pressure is inside here. So the pressure at the starting point, so let's say somewhere here, and the pressure here is constant throughout the cross-section. So that means that according to Bernoulli's equation, your velocity throughout the whole cross-section of the pipe should be uniform. But it is not valid for the Hagen-Poiseuille flow, because the velocity is zero near the sidewall of the pipe and is maximum in the center of the pipe. So that really requires for some distance to establish this new flow. And this distance A is the distance which is required to make this invalid. Okay, so that's about physics. So actually in physics there are two different stuff. One of them looks like mathematics. So you need to derive something, you integrate, differentiate, and do. But there is another very important part of physics which requires you to understand what is actually going on. Because in the case of, like, for example, mathematics, as long as you are able to write or do these calculations, you get the correct answer, and that's nice. But in terms of physics, you can get the formula, but for some reason this formula fails to describe your real situation. And you need to understand what actually is going on with these equations. And sometimes I would say that qualitative knowledge of what happens in your system can be more important than quantitative knowledge. Quantitative knowledge allows you, like, for example, to compare the results of the experiment with the calculation, with the predictions. But the quantitative knowledge cannot replace completely the qualitative understanding. Because the physics today is much more complicated than what I have shown you here. And if you, for example, are pretty much focused on the quantitative or mathematical stuff, you can easily, like, make yourself a fool if you try to apply your great and rigorous mathematical model in the conditions where it is not applicable. So you can get some unphysical results. Okay, and well, by the way, actually, about the physics of hydrodynamics, this is considered one of the most difficult subjects. And you even can, well, I say that every year, but once again, you can win $1 million for this. And there is a problem published by Clay Institute of Mathematics, and it says that $1 million should be delivered immediately to any person who rigorously proves that Navier-Stokes equations, which are actually the equations which describe flow of fluid in the most general conditions, have the solution and have only one solution. And if you are able to do this, then $1 million is yours. No one was able to do this so far, so please consider it. I would be happy to have this too, but well, I'm not specializing in hydrodynamics. I specialize in quantum stuff, so I cannot do this. Okay. Now let's go further with this Bernoulli equation. Since we have started with this, I would like to add something more to this, because if you look through the derivation, I have said that this Bernoulli equation is valid for any streamline. So this is constant through, so at the streamline. Basically, this means that, for example, if you have some motion of fluid which goes around some object, this Bernoulli integral can be different for different streamlines. For example, for these streamlines, it can be different from this streamline. This becomes very important when you deal, for example, with planes, because planes have these engines, yeah. So in the engine you have a ventilator. Okay, you have some combustion there, and that means that engine pushes the air out of it, so it grabs some air and pushes it further. So it's on a very basic understanding of what engine does. And well, that means that actually the streamlines of air which go through the engine and the streamlines which do not go through the engine, they may have different value of this Bernoulli constant from Bernoulli equation. So that's the first one. And there is also another nice example which allows you to understand the limits of Bernoulli equation. The example is as follows. let's say this is tornado. In the tornado, you have a circular motion of air. So there is something which is moving along the Earth, and there is a circular motion, and it goes like this. So it brings about devastation to everything, which means to everything it meets on its path. But I would like to have a more interesting discussion about tornado. Let's look at the distribution of velocities from the above. So let's assume that I have a perfect cylinder here which rotates. And if I look at this from the above, that means that my velocities of the air go like this. So actually that means that there is a center of the tornado in which there is no velocity, because this is a rotational motion. The speed of the rotational motion is proportional to the distance from the axis. So it goes like this. And let's say I want to answer the question. So it becomes larger, but at some point the tornado ends up, so then the velocity decreases. So in a certain region, I have velocity equal to omega times r. So no velocity here. So the question is, where the pressure is maximal? The pressure of air, where it is maximal in this condition? It might look like that it would be a great idea to apply Bernoulli equation, which says that P plus rho v squared over 2 is constant, and that means that the pressure becomes lower as I go further and further from the center. That's wrong. And that is wrong. Because as I said again, this equation is applicable to the streamlines, and that means that probably this streamline which is closer to the center and that streamline which is farther away from the center, they have different constants in this equation. And let me show you how it is wrong. It can be done from just the dynamics viewpoint. So first of all, let's consider a portion of air which moves along in this circle. So I have different pressure forces which go from different sides of this, and so let's magnify this image here. So it goes in this direction. I have pressures from all sides. Okay. Along the streamline, this is constant, and along the streamline, I actually have constant velocity. So that means that pressures which go from this side and from this side are equal to each other, so they cancel each other out. So there are these two pressures, and actually they don't cancel each other out. And the reason for that is that due to the circular motion, I have a centripetal acceleration. So I have an acceleration in this direction. Okay, that brings me to another remark. Well, probably you all understand this, but acceleration, by definition, is the rate of change of the vector of velocity. And since velocity is a vector quantity, it has magnitude and the direction. So you can change velocity in two ways. You can change the velocity by changing its magnitude, so by changing speed actually. So magnitude of the velocity vector is speed. So by changing speed, you have acceleration. But you can also have an acceleration which doesn't come from the change of the magnitude of the velocity, but which comes from the change of the direction of the velocity. And this is actually this centripetal acceleration. Because when you have a uniform motion around the circle, the magnitude of the velocity remains constant, but there is acceleration due to the change of the direction. Okay, so in here I have this acceleration, so that means that pressure forces are not canceling each other out. So that means that the pressure here should be greater. So P1 and here P2. So P1 should be greater than P2 in order to dynamically to give some acceleration to this portion of air. So that means that follows from the second Newton's law. So that force equals to ma. So that means that P1 minus P2 times, okay, dA equals to dm, which is the mass of this small portion of air, multiplied by acceleration, which is equal to v squared over r, where r is the distance from the center. Okay, so that means that I have the pressure difference, and that actually means that as I go farther away from the center of the tornado, my pressure should increase instead of decreasing. So the Bernoulli equation becomes terribly wrong in describing tornadoes. The pressure is minimal in the center of tornado, and that is actually what can be seen, because, for example, some cows or houses are being lifted up by the tornado into the air. And this is the reason for that, because there is this large pressure difference. And the lowest pressure is in the center. Okay, so now let's discuss the following subject. So we are now having a qualitative discussion of iron hydrodynamics, as you see. Like I showed the examples where these equations are no longer valid. First, I have started by showing that Hagen-Poiseuille equation is not valid at a large Reynolds number. The second is that where Bernoulli equation fails to describe the situation. And now the following example is the lifting force of the wind. I think this one is the most difficult example, because there exist so many of qualitative explanation of the lifting force. There are so many, and so many of them are actually wrong. Okay, one of them says that, okay, it's simple, that like the incoming flow goes like this, the outcoming flow goes like this, so you have a momentum change in between here and here, and that produces a lifting force. That is partially valid, but it doesn't explain in any way why D'Alembert paradox is not applicable to this one. Why? You have a momentum going in the downward direction after the wind. So I would say that this is the first explanation, and there are some questions which can be stated and which can be asked to this explanation. Okay, there is slightly better explanation which uses Bernoulli equation, and it says the following. That for some reason, we don't know yet for which reason, but for some reason, the air moves slower below the wind than above the wind. And since you have P plus rho v squared over 2 equal to constant, that means that where the speed of air is larger, then the pressure is lower, and here is larger, so that gives you a push. And again, the lifting force. This example shows you that not everywhere where you have the larger speed, not everywhere the pressure would actually be smaller. Well, probably that can be explained that, well, far away from the wind, all of the velocities of my air are approximately the same. So if I consider the streamline here, the streamline which goes this way, so that means that actually if I calculate this P plus rho v squared over 2 for the streamlines above and below the wind, then that would be indeed constant in here. So that means that this should be constant also for both of the streamlines. So that actually is better, because that shows that actually this tornado condition is not applicable to this wind. But that assumes that we don't have any engine. Because I have said, when you have engine, then different streamlines would have different Bernoulli integral associated with them. So it says so it might be applicable to gliders, which don't have any engines. And now we also need to understand for what reason. For what reason is the velocity above the wind is larger, okay, not the velocity but speed, so the magnitude of the velocity. The speed above the wind is larger than the speed below the wind. So this explanation doesn't give you any reason why this speed should be larger than this speed below. And well, there is actually one trick which allows you to avoid this question by stating that, okay, so if you look like at the wind profile, it says that if you go around this path is longer than if you go along this path. And there is a hypothesis which is called equal time hypothesis that it takes the same amount of time for the air particle to move from this side of the wind, from the front of the wind to the end of the wind along each of these paths. So, and since the upper path is somewhat longer than the lower path, that means that you require larger speed to get this travel at the same time. But the problem is that this hypothesis is wrong, because actually the time which it takes to travel for air molecules along this path and this path is different, and it takes it takes much more time to travel along the bottom part of the wind. So if I look, for example, okay, now. If I, for example, look at air particles which initially start over the same plane, and I look at them going around the wind at different moments of time, it turns out that actually the air particles which move along the upper part of the wind already come to the end of the wind, but while these particles at the bottom actually move even slower than that. So that means that the difference in the speeds is even larger than predicted by this equal time hypothesis. And that is an established fact. So this explanation, although it says that there is difference in speeds above and below the mean, it doesn't explain due to which reason this difference of speeds actually emerges. Okay, so now let's try to do something like tornado explanation, and I have seen that, and probably I think this one is the most convincing. It says the following, that if I have a streamline which has a curvature, then if I go in this direction, that would be the direction of the pressure increase. So as long as I have this curvature, because along the curvature, all of my air particles would have a centripetal acceleration, and that means that the pressure above would be somewhat larger than the pressure below. And in here too, this is a direction of the pressure increase. But far away from the winds, the flow of air is not curved anymore, and in here, I can say that in here I have atmospheric pressure. Below here, I also have atmospheric pressure. So if I go from this direction towards the wind, I would have pressure increase. So in here, I would have P0 plus some delta P below the wind. But if I go from this streamline towards the wind, that would be the direction of the pressure decrease. So I would have P0 minus some delta P. Oh, it can be the other quantity, delta P1, delta P2. But the pressure above the wind is lower than the atmospheric pressure at that height, while the pressure below the wind is larger than the atmospheric pressure at that height. So that explains you the origin of this pressure difference in this way. But now we also need to understand how to go around with D'Alembert paradox, even with this explanation, because this explanation, well, it works pretty much nice. But if I look at the solution which would be obtained by D'Alembert and his contemporaries, it would go like this. But actually the flow would go as follows. So there would be no change in the momentum, so the first explanation would fail. And also, it would go like this, and in here there would also some pressure differences, and every pressure difference would be compensated, and no lifting force would be if I have the D'Alembert flow around my wing. So the explanation why this actually doesn't happen is the phenomenon which is called boundary layer separation. So let's look at this part of the trajectory in the D'Alembert solutions of the flow of air around the wing. So in here I have a very small curvature radius, so that means that we have huge pressure difference which would be required to keep this flow attached to the wing. But actually there is nowhere we can take these large pressure differences. So what actually happens is that the boundary layer here separates from the wing and goes in that direction, instead of moving around the wing and going according to D'Alembert solution. And the same stuff happens with this kind of a flow. So it continues going in this direction. So it's more natural to move in that direction than go around the wing and without producing any kind of a lifting force. And probably I feel like that all of these explanations are wrong, but I think this one is somewhat closer to the truth than any other one. Because it at least explains where this pressure difference emerges from. It doesn't rely on the hypothesis that the air speed above the wing for some reason is larger than the speed below the wing. So it actually is a consequence of these pressure differences. So when you again apply the Bernoulli equation, then you would get that. Okay. So that means that hydrodynamics are really quite complicated subjects in which sometimes some minuscule stuff like viscosity can play a major role. Even though the viscosity in here is not so large to make Bernoulli equations invalid. So Bernoulli equation is approximately valid when you go around the wing. But, well, nonetheless, it is required to obtain the lifting force.